Okay, the last part of this chapter is to show the second order conditions. So we first show the second order necessary condition and then the second order sufficient condition. And after that, we give a few examples. Okay, the second order necessary condition is actually pretty similar to the second order necessary condition for before. We have only Ecoli constraints. So the conditions are given as follows. Suppose we have objective function f to be minimized, and the g, h, there are inequality and equality constraints. Assume that they are OC2, meaning that they are differentiable. They're differentiable, and then up to the second order derivative, they're all continuous. And then if x star is a regular point and the local minimizer of f over the domain specified by the two constraints, then there must be a lambda star in Rm, where m is the number of inequality constraints, equality constraints in H, and also the mu star, which is the number p is the number of inequality constraints in G, and this mu star is greater than or equal to 0, such that first of all, the first order necessary condition must be satisfied. And that condition is known as the Kkd condition, as in your previous lecture. Okay, so those conditions for the Kkd condition, Kkd conditions must be satisfied. And the second order information come from the second item here. The for all the y's in the tangent space x star, where this tangent space x star is specified as the y's that are perpendicular to all the gradient h at x star and all the gradient g at x star, where this g only referred to the active constraints. So as we said in the previous lecture, we say that we can combine the gradient h of h1 x1 h1x all the way to gradient hmx. Right, that's what we have for the equality constraints, and also include the active inequality constraints, which is gradient g. For example, in the previous lecture, we said about an example where we have three inequality constraints, g1, g2, g3, and only the first two are active, meaning that g1 at x star is equal to 0, g2 at x star is equal to 0, but g3 at x star is smaller than 0, strictly smaller than 0. So in that case, we will ignore the inactive constraints, but only include the active constraints. So in that case, we only include these two, right? And then this altogether form this. We can consider this in place of the Jacobian matrix of H. So this first part is the Jacobian of H, but this part is like the Jacobian of G, but only for the active constraint G. And then the span of this row space, we know that this is the space, the orthogonal complement of this space, the row space here, is equal to is called this Tx star. So the Tx star is all the y's that will multiply y to this matrix, you get 0. Okay, we multiply y to this matrix, you get 0. So these are all the y's that we're going to put in this T. So this is like the tangent space. So for all the y's in this space, this is greater than or equal to 0. So this part is the Hessian of the Lagrange function L with respect to x only. Okay, and in this case, the lambda star and the mu star are fixed. We take the gradient, second order gradient of L, actually the Hessian of L, with respect to x, then we get this matrix. So this matrix is actually n by n matrix. Okay, since lambda star and mu star are like fixed. Then we take the Hessian of L with respect to x and then plug in x equal to x star, then I'll get an n by n matrix. So all the y's that are make this greater than or equal to 0, then we can say this is the necessary condition for x star to be a local minimizer. Okay, so this is actually the proof. Actually, is very similar to the one we had with equality constraints only, because right now this we only consider we're actually considering the local minimizer not just on omega but also on the subset of omega, which is the omega prime we said earlier. Okay, the omega prime is that's what I said. The omega prime is defined as all the points in omega such that the hi of x is equal to 0 for all the I from 1 to m, and all the gj of x is equal to 0, all the active constraints where j is in this. Okay, so this is a subset of omega. So if x star is the local minimizer over omega, there must be also a local minimizer over omega prime. And then we know that within the neighborhood of x star, all the inequality constraints remain inactive constraints remain inactive. So within the local neighborhood, we're still inside here. And so we can just consider the Kkd condition or Lagrange condition over the omega prime. And that gives us this last one, this one here. So this is the same as the second order necessary condition we set for that case where we only have equality constraints. But right now it's like that case because we only have equality constraints for this omega prime. Okay, the only thing that you need to be careful is that since we actually have inequality constraints, but it's just that some of the inequality constraints are active and they become equality constraints. So this T only contains those G, gradient G's. All right, so that's the second order necessary condition. Right, the proof is pretty, it's just the same as before. It's just by realizing that this become equality constraints. Okay, so we will not give much more details on that, but you can easily derive from that. Okay, so that was the second order necessary condition, which used the Hessian of L, and we can also derive the second order sufficient condition. And that is also similar to what we did before, and there's a subtle difference that I want to point out soon later. But now let's first see what this condition is. So again, similar as before, this f is an objective function, inequality constraints. Equality constraints, there are OC2 in the if there exists a lambda star and mu star, the Lagrange multiplier and the Kkd multiplier, such that the first order necessary condition is satisfied, so meaning that x star is a x star lambda star mu star is a Kkd point and it satisfies all the Kkd conditions. That's one. The second one is that for all the non-zero y in this T tilde, in this space, this is strictly greater than 0. Okay, so this part is the same as the second order necessary condition, where we take the Hessian of L with respect to L, with respect to x, but this y is not the one here. It's not the one from this set. Okay, instead, this y is from this T tilde. What this T tilde is? We first need to decide what is the j tilde of mu star. We know that j is x star. This is the index of the active inequality constraints. For example, in the previous example, we will have 3 inequality constraints. The first two, G1, G2 are active. The G3 is inactive, is strictly less than 0. Then this J contains 1 and 2 only. But this one is a subset of that, because we said that for active constraints, mu1, mu2, I know that for inactive constraints, Gj, for example, for G3, if it's less than 0 at x star, then, so we'll say, if Gf or G3 x star is less than 0, I know that mu3 star must be equal to 0. So that's no problem. But for G1 x star equal to 0, the mu1 star we just need to be greater than equal to 0. It could be 0, it could be non-zero. Okay, or it could be 0, it could be positive. So we don't know the sign yet. And here this J tilde is just selecting those that are actually strictly greater than 0 for those active constraints. So that means if mu1 star although the G1 of x star is equal to 0, it's active, but the mu1 star is equal to 0, then we'll still remove it from this to form this set. Okay, so this is actually a subset of J star. So we have fewer index in this J tilde. And then this T tilde is all the y's, all the vector y's, such that this is the same as before. The y must be perpendicular to the row space of the Jacobian of H. At the same time, the y is perpendicular to all the Guiden GJs, where the GJ is active. But not only that, the corresponding mu j is greater than 0. That means the j must be in this set, or in this set we just defined. Okay, so for example, let's say if we have, let's just say that g1 of x star is equal to 0, g2 of x star is equal to 0, and g3 of x star say is less than 0, then we know that the corresponding mu3 star is equal to 0. That's for sure. And the mu1, say mu1 star, we know that it just needs to be greater than equal to 0. But if it happens to be equal to 0, the mu2 star is greater than 0. So although these two are active, but the one of them is corresponding to a mu1 star equal to 0. The other one is corresponding to mu2 star greater than 0. In this case, the j tilde of x star, mu star. The reason why we include mu star is that it's just not, it doesn't only depend on x star, but also depend on the sign of mu star. In this case, it's just equal to 2. Okay, so it's a subset of j of x which is equal to 1, 2. Okay, and then the T tilde is defined to be this set. Okay, so the y needs to be perpendicular to this gradient to the Jacobian of H, but also the gradient G2, not G1 anymore. Okay, it could be inner product of y and the gradient G1 could be non-zero. Okay, so that's this T tilde, and now you can realize that this T tilde is bigger than the Tx star we said earlier, because this Tx star, according to the same example, the y must be perpendicular to both the gradient G1 and the gradient G2. But in T tilde, it only needs to be perpendicular to the gradient G2, so it has less requirement on the y. So this is actually a larger set. So it contains Tx star. Okay, it contains Tx star. So we need to show that this is greater than 0 for all the y in this larger set. So that means we have actually stronger condition on this matrix. Okay, and this is a sufficient condition. So if we can find some x star such that this hold, this is hold, and this is the hold for all the y's in this T tilde, then we can claim that x star is a strict local minimizer. But this condition is only sufficient. If you cannot verify these conditions for x star, it doesn't mean that x star is not a local minimizer. It could still be a local minimizer. Okay, and this is because this is only a sufficient condition, not necessary. Okay, so that's the second order sufficient condition. Okay, now let's give several examples. The first example, suppose we're trying to minimize the x1, x2 square. This is our objective function, and we have two constraints, one equality constraint x1, x2, and then we have an inequality constraint for x1 greater than or equal to 0. So apparently we can define this to be f of x as this, and we can take x1 minus x2 as the hx. So that's this equality constraint. We only have one equality constraint, and also can take a g1 to be negative x1. Then we have gx less than or equal to 0 will give us this last constraint. Okay, so we get a standard form, and then we can take we can first write down the Lagrange function, which is just the f of x, this f of x, plus h times lambda times hx. The lambda is a Lagrange multiplier, and then mu times plus mu times gx, and that gives us this. Mu is the Kkd multiplier. Okay, that's the Kkd multiplier. And then we can find the Kkd conditions. The first condition is as we said, it's just taking the gradient with respect to x. Now we have x1, x2, so we take the gradient with respect to x1, x2. We get the first one as take the gradient with respect to x1. Then we have this, right, corresponding to that one, and then lambda, and then for this one we get 0, and then this one have negative mu. So this must be equal to 0, and the derivative with respect to x2. Then this gives us 2x1, x2, and negative x2 and negative lambda, and then 0. So that's why we have this. And we also have the gradient with respect to lambda. And that's actually just the Ecoli constraint, as we said. After this first two, which is the gradient of L with respect to x, this one is corresponding to hx equal to 0. And this one is corresponding to gx less than equal to 0. Okay, and then this one is like mu greater than equal to 0. And this one, last one, is mu transpose gx is equal to 0. Okay, so that's the Kkd condition, first order net-zero condition. All right, so that's why we have these conditions. And now let's see, we have 4 variables to solve for: x1, x2, lambda, and mu. And we do have 4 equations, so it seems that we have a good chance to solve for them. And in this case, let's see what are the solutions. Okay, let's first check the case where, so I should add the solution here. First, let's check the case where x1, x2, since these two are equal, so x1, x2, they are equal. They are both equal to 0, or they are both to some other non-zero value. So suppose they are both equal to 0, we can check. If they are both equal to 0, then this is okay. This is okay, and lambda can be any positive number. But if x1, x2 are both 0, then this is 0. That means lambda is equal to 0. Okay, and the lambda is 0, this is 0, and so mu is also equal to 0. So apparently, all of them, x1, x2, lambda, mu, they're all 0. This is the one possible choice. Okay, and then we also check the case where x1, x2, they're non-zero. So if x1 equals to x2 but is non-zero, then mu must be 0. Let me see that. Yeah, then the mu must be equal to 0. If mu equals to 0, then we will have if mu is equal to 0, then we have x2 squared plus lambda equals 0. We have 2 times this, but x1, x2 are equal, so this is like 2 times x2 squared minus lambda equals 0. So when I add these two, we'll get 3x2 squared equal to 0. That implies x2 equals 0. Then that's not possible, right? Because we said x1, x2 are non-zero, so that's not possible. So it appears that the only choice is this. So the x1, x2 are zeros, the mu and lambda are 0 as well. This is the only point that satisfies the Kkd conditions. Okay, so it satisfies the first order condition. Now let's check the second order condition. Okay, because the mu star is equal to 0. So if mu star is equal to 0, that means when I consider the t tilde, I should consider the gradient h. Now I only have one h, so that's just gradient h, x equals to 0. So that's the gradient h, the hx equal to 0. So that's the only row. And now let's consider if I should add the gradient g, because the corresponding mu star is equal to 0. So that means the like the previous example, like this one, although the is active, I believe at that point it's active. If we plug in 0, 0, then apparently it's active because x1 is equal to 0. at that point. So this constraint is active, but it's active. Although it's active, the corresponding the mu star is also equal to 0. So in that case, we'll kick it out from the set of active points. With this G tilde will not have that. We will not have this corresponding G. We will not include that index. So that means my T tilde of x x star mu star will be the set of points y in Rn such that this gradient h of x star transpose y is equal to 0. Okay, you will not have the g there. Okay, this is the T tilde. It just means the all the vectors that are perpendicular to gradient h x star. But the gradient h, remember the h, x is x1 minus x2. So the gradient h x star at transpose will be apparently it should be 1 and negative 1. Right? It's actually this value for every x, not just x star. Because we take the partial derivative, which is 1, negative 1. So this is the gradient h x star. So I need to find all the y's that are perpendicular to this vector. So that means the two components of y must be equal, right? So that's why this y is nothing but just this. Okay, you can also derive from here. This is telling us that this is the null space of the gradient h, means that all the vectors multiplied to this are given us 0. It's null space of this, and this gradient h is just this. Which is null space of that. And null space of this matrix, you can treat it as a 1/2 matrix, is all these vectors. Okay, or all the vectors looks like this for t, any value of t. Okay, and then we can also check the Hessian with respect to x. So the L was this. So we can take the gradient, we'll get that. We'll get this one. And then we can take the Hessian. That means for the first one, I'm going to take the gradient with respect to x1, x2. So when we take the gradient with respect to x1, I'll get 0. For x2, I'll get 2x2. Okay, for the second row, gradient with respect to x1, I'll get 2x2. And the gradient with respect to x2, I'll get 2x1. So this matrix is my Hessian of L with respect to x1, with respect to x. Okay, that will be this. And then we plug in x star, mu, lambda star, mu star. Apparently this doesn't depend on lambda star, mu star, but in general it will be. Okay, and for this x star, which is 0, 0, then we just get a 0 matrix. That means we'll just get that. Okay, so we get that. Now we just need to check if I multiply any vector from this space or any vector of this form to the left and the right and see if the result is strictly greater than 0. But apparently we don't need to do that since this is a 0 matrix. So no matter what vector I multiply to the two sides, I will always get 0. So it doesn't. So the second order sufficient condition, like this one, is not satisfied there, since we just get equal to 0. So it's not satisfied there. So that means the second order sufficient condition does not hold. But as we said, it's a sufficient condition, so it's not necessary. We still cannot claim that it's a strict local minimizer. But for this particular case, actually, if you look closer to this problem, it has a trivial solution, or it can be solved trivially, since the x1 is equal to x2. So I just can replace the x2 squared by x1 squared, for example. Then I'm minimizing x1 squared subject to the constraint that the x1 is greater than or equal to 0. So x1 cube. So that's what I'm really minimizing is x1 cube subject to the constraint that x1 is greater than or equal to 0. So you know that x cubed looks like this, right? This x1 cube is like this, and then you want it to be greater than 0. So apparently the strict local minimizer is here, so which is 0, and that is the 0 we found earlier. So it does a so this point is actually, it's a Kkd point. It doesn't satisfy the second order sufficient condition, but it's still a strict local minimizer. Okay, and actually it's a global minimizer as well, because as you can see, that is since we're considering this side only, so this is the global minimizer. Okay, this also says that this is only a sufficient condition. Okay, so that is one of these examples. The second example, let's say we are given a constraint optimization problem where the objective function is this, and the constraint is that this is greater than or equal to 4. Okay, now apparently we're going to set this as f, and we're going to set this minus 4, or 4 minus this, to be g. Okay, because I want this gx to be less than or equal to 0. Okay, so that's my inequality constraint function. This is my objective function. Now I can form the I can write down the Lagrange function, which is this f plus mu times g. Okay, so mu is a non-negative scalar. The g is this function, so that together is this. And then we can write down the Kkd condition. The first to take the gradient with respect to x. So let's check with respect to x1. I got 2x1, just according to this. This is the 0, it's 2 mu minus 2 mu x1, then that's it, right? That's for this row. And then the partial derivative with respect to x2. So 8x2, and this is nothing, and then we have a negative 4 mu x2. That's this. Okay, and then we don't have a equality constraint, so only inequality constraint, and this will be gx less than or equal to 0. This is mu greater than or equal to 0, and this one is mu transpose g. But right now, both of them are just scalars, so they're just the product of these two is equal to 0. So that's this. Okay, so this is the Kkd condition. Now let's try to solve for it. Okay, now let's again, let's say we have 3 variables, x1, x2, and mu, and we do have 3 equality constraints. So we have the hope to solve for these 3 numbers. And let's see. Again, we're going to consider the solution for a few cases. For example, if mu equals 0, then this is gone, then the x1, x2, they are both equal to 0. But if they're both equal to 0, I'll have this equal to 0, which cannot be greater than 4. Right? So that means mu cannot be 0. Okay, so now if mu is not 0, we'll consider 2 cases. One is that mu equals to 1. The reason we consider that as a special case is because if mu equals to 1, then the x1 can be anything here, right? But for x2, if mu equals to 1, then we'll have this side as 4x2. Now is equal to 0 means that x2 must be equal to 0. So x2 must be equal to 0. x1 can be anything so far. And for this one, I know that x1 must be greater than or equal to 4. So the x1 square must be greater than or equal to 0. And the last one, since we said the mu equals to 1 and x2 equals to 0, so the last one says that x1 minus 4 must be equal to 0. Okay, so in this case, x1 must be equal to 4. So this is greater than 4. So x1 must be equal to 4. So that's the case where mu equals to 1. So if mu equals to 2, then this will be just equal to 0 no matter what x2 is. But when mu equals to 2, this will be this side will be negative 2x1 equal to 0, so x1 must be equal to 0. So from there, we know that this must be equal to 0, then this is greater than or equal to 4. Okay, and that means x2 squared is greater than or equal to 2. So that's 1. So the x2 squared will be greater than or equal to 2. And because mu equals to 2, x1 equals to 0, so here I'll have 2x2 squared minus 4 equals to 0. So that means x squared must be equal to 2. Okay, and the x2, then x2 can be positive or negative root 2. And x1 is 0. So these are all the possible cases. Okay, so now let's summarize. Oh, sorry, that's for the cases that I just went through, mu equals 1 or 2. If mu is not 1 or 2 or 0, then this will give us some non-zero number times x1 that is equal to 0. And this gives us some non-zero number times x2 that is also equal to 0. That means x1 and x2 are both 0. But that will violate this one. That is impossible. So the mu cannot be any non-zero value other than x1, x2. Okay, so in summary, we said that when mu star is equal to 0, then these two are both equal to 0, but it violates this, so that's not possible. And then if mu star is equal to 1, we can get this one solution, I think. Yeah, I missed the 2 here, so it should be 2 here. Okay, so it should be the 2 here. So x1 could be positive, negative 2. And then x2, when mu star is equal to 2, then we solved for this, and we know that the solution could be this. And if mu star is greater than 0, we know it's greater than or equal to 0. So we consider these 3 cases already. So it's greater than 0, but it's not equal to 1 or 2, then we get x1, x2 equal to 0, which violates the Ecoli constraint. So that means only these 2 are possible. So now we have 4 choices. When mu equals to 1, we have 2, 0, or negative 2, 0 for x1, x2. And if mu equals to 2, then the x1 must be 0, but x2 could be positive, negative root 2. Okay, so we have 4 choices. So these 4 points satisfy the Kkd conditions, and the local minimizer must be from them. Okay, now let's see. Let's check the second order condition. So for the second order condition, we need to know several things. First is that we can take the Hessian of L with respect to x. So the Hessian, let's go back. That is the gradient, right? It's a gradient, so we need to take the Hessian. That means the Hessian of L with respect to x at the point x, lambda mu is equal to the first one. First row is the gradient of the first gradient of the dl dx1, right? So that will be the gradient of this, and that gives us 2 minus 2 mu, and then 0. And similar, second row give us 0, 8 minus 4 mu. So that's the gradient, that's the Hessian of L with respect to x. Okay, now let's check that. We rewrite here. The Hessian x lambda mu. We don't have lambda actually because we don't have the Ecoli constraint. We have this. Let me just remove the lambda, it doesn't matter. So this is equal to, remember that this is equal to four times two minus 2 mu, 8 minus 4 mu. Okay, so that's the Hessian. And so when we plug in mu equals to 1, we will get this. When mu equals to 1, then this is just gone, and then we have 4 here. So that's this. And then we also need to figure out the G, gradient G. So remember that the mu equals to 1, so that means we should include this into the T tilde. So the J tilde will only include this, and the gradient G right now is equal to, let's see, what's the G? G is this. So the gradient of G will be, let me first write it down, the gx is minus x1 squared plus 2x2 squared minus 4. So the gradient gx is negative 2x1 and negative 4x2. Okay, so when we plug in plug in the point x equals to 2, 0, I will get negative 4, 0. We'll plug in G negative 2, 0. We'll get 4, 0. Okay, so that is the gradient G. So probably I should write this as this instead to be more precise. But that doesn't matter because that's only need to give us the T tilde. So the T tilde right now it should be all the points, so all the y's, such that the gradient G of x star transpose y is equal to 0. This is my T tilde. But the gradient G is this. It's either this or this. So if it's this, for example, if at the point x star equals to that, if x star is this, then the y should be, I want to multiply y to this vector, I get 0. That means the first component of y must be 0. Second component of y could be anything. Okay, so that means the y is this form. Is anything more like this. T can be any real number. And similarly, if x star is this, this space is the same because the y is also like this. Okay, so this is the T tilde. The y is a form of this for any arbitrary t. Okay, now we have all the ingredients. We know where we can choose the y from, and we know what is this the Hessian of L with respect to x, which is this. So now let's pick up any non-zero y from this set, or any non-zero y like this form. In this case, t will be non-zero. So when we multiply this to this matrix, we'll get, so basically just this one, right? And it's equal to t01 or 0t. Let me just write it as 0t. So the row vector y is 0t times this 0004, and then this is 0t. Okay, and this is equal to 4t squared. Okay, since t is non-zero, this must be greater than 0. And that means this x star, either at this point or this point, the second order sufficient condition is satisfied. So that means these 2 points, 2, 0 and negative 2, 0, they are strict local minimizers since they satisfy the second order sufficient condition. Okay, and that's for that. And then we can consider the other 2 points, right? For mu equals to 2, I should say equals to 2. We have we know that the x star will be 0 and the positive or negative root 2. So this is x1, this is x2. And then we can calculate the gradient, the Hessian. So again, recall the Hessian is that. Hessian is this. So when we plug in mu equals to 2, then this will be giving us negative 2, then this will be 0. So that's our Haitian, which is this. And then the gradient is the same as before, and then we're going to plug in this 0, positive, negative root 2. Okay, and then here the gradient gradient g is this. So plug in 0, positive, negative root 2, we'll get 0 and positive, negative 4 times root 2. And similarly, the null space of this matrix, or this matrix, you can treat as a row vector. Or all the vectors that when you multiply this to this, you get 0. That is the set of vectors like this. Okay, the first component must be can be anything. The second component must be 0. So when we multiply these two vectors, or taking the inner product of these two vectors, we get 0. Okay, so that means the T tilde is the set of vectors like this. And then we can check that's this quantity. And then again, this y is of this form, T0. And then so I have the T0 times the Haitian, which is the negative 2, 0, 0, 0. And then we have the T0. And then when together, we have negative 2t squared. And because t has to be non-zero, so I know that this must be less than 0. So that means the it's not sufficient second order sufficient condition as we posed in the theorem, but it's because we wanted greater than 0. So that means the second order sufficient condition for strict local minimizer. But this is less than 0, which means this is a strict local maximizer. All right, so that is the property of these 2 points. Actually, they're strict local maximizers. Okay, so that is that completes the example here. Okay, so this should be, if you like, it should be this way. Okay. Okay, now we started talking about a important class of optimization problems that are called convex optimization problems. Okay, so first of all, we need to define the a convex set and the convex functions. So these are the key components for a convex problem. A set is called convex if for any 2 points, it's called convex if for any 2 points in the set, this linear combination of the 2 points is also in the set. But this linear combination is not arbitrary for the alpha. The alpha needs to be between 0 and 1. Okay, so the meaning is that we have a set like this. Then this is the x, this is the y. Then this alpha x plus 1 minus alpha y. You can see the alpha is a scalar between 0 and 1. So when alpha is equal to 0, then we can see that this is just equal to y. When alpha is equal to 1, then this is equal to x. Right? So that's for the alpha. That's where this point is when alpha is equal to 0 and 1. When alpha is between 0 and 1, this is the point between these two points. Okay? So what this means is that if you have these 2 points x and y, then a point in between is just alpha x plus 1 minus alpha y. Okay, x and the y are vectors, alpha is a scalar. So this is a point in between. And what this means is that as long as you have 2 points in the set, then the entire line segment between these 2 points is also in the set. Okay, and apparently this will be a convex set. Something like this will be also a convex set because no matter which 2 points you choose, the line segment between them is still in the set. And this, however, is not a convex set because you will choose this point and this point. Then when we make a line segment between the two, some part will fall out of this set. Okay, so only if for any 2 points, the line segment between them is completely in the set, then the set is called convex. Okay, So now, given the definition of a convex set, we can further define the convex function. So convex function is always defined over a convex set, where the following property or following inequality holds for any 2 points x and y in the set, and any alpha between 0 and 1. Right? So what this function means, you probably know this from calculus, that a function is convex means that it's something like this. Right? So if this is the x, this is the y, then the left-hand side here means the function value, the function evaluated at some point in between these 2 points. Okay, so say for example, this is alpha x plus 1 minus alpha y. All right, and then the function value will be here. Okay, that's the left-hand side. The right-hand side is this combination of f of x and f of y. Okay, taking this combination of f of x and f of y, and if I draw this, maybe I put this direction as the value for y, then this point is here. Okay, so this point which is on the curve is this left-hand side. It's left-hand side, which is this. It's left-hand side. And this is the right-hand side, which is this point. And what this for a function f to be convex, then it needs to be defined over this convex set, so that for any 2 points in the set, this point here makes sense, because this point is some point on the line segment between these 2 points. So since omega is a convex set, this must be in omega as well. So that's f is actually defined there. Okay, make sure that f is defined there. At the same time, the function value at this point is smaller than or equal to this value. Okay, and that is like the line segment connecting these 2 points, 2 function value, is higher than or bigger, is greater than or equal to the value here. So the right hand side is greater than or equal to the left hand side. Okay, so that's the that's for a convex function. Okay, this is the 1D case, but in a 2D or high dimensional case, say if this is a space for x1, x2, this direction is for the function value, then the convex function looks like this. Okay, it's like a bow shape, and it's kind of facing up. Also, it's either this or it's like always decaying, but it's sliding down. Okay, on that in that some sense, it's like that for 1D case. Then the function looks like this, or looks like this. They're all convex. Okay. Now this is the definition for convexity, and there is also a name called strictly convex. Strictly convex means that for any 2 point, one point in between these 2 points, actually strictly in between these 2 points, not x or y, but some point in between, the function value of this is strictly smaller than the function value there. Okay, so this is just in contrast to just to exclude such kind of function. For example, if you have a function that looks like a straight line, for example, then for the 2 points x and y, the function value, sorry, maybe I should point it here. This is the alpha x plus 1 minus alpha y, and the function value corresponding to this point, which is the left-hand side, but also equal to the right-hand side. You can easily check that. Okay, for this point. So in this case, the function is not strictly convex. It's just convex, but not strictly convex, since we don't have this strict inequality. Right? And also we can define concave functions. A function is concave if and only if negative f is convex. Okay, so the convex function, we saw that for 1D case, the convex functions look like either this or this, or something like this. Okay, these are convex functions. And for concave functions, I will look like this, or this, or this. Okay, because you take the negative, they will flip it down, and they will be convex functions. Okay, so this is concave functions. And strictly convex means that, as I said, you don't have a really flat area. The curve actually looks like banded, always banded somehow. Okay, either this or this, just always banded. Not, you don't have any flat area. But by the way, these kind of functions are also convex, but not strictly convex, as I just mentioned, because they are not strictly banded, but somewhere. Okay, somewhere it's just a flat, or it's linear, or it's affine. Okay, that's for convex functions, strictly convex functions. So another equivalent definition for a function to be convex is based on the definition of epigraph. So we first define the graph of a function is just either the curve or the surface, depending on the dimension that you have, the collection of points like this. Okay, so for example, if the function f is a univariate function where n equals to 1, then the function looks like this, right? And so this curve is called epigraph. So if this is the x, this is the f of x, then this curve is called epigraph. If it's 2D, then say this is the x1, x2, this is the f of x. Then you have a surface, as I just drawn, like this ball facing up. Then this is also this surface here is the graph. The epigraph is the area above the graph. Okay, it's this area. So everything above it is the epigraph, and for this case, everything above this surface is called epigraph. Okay, so it will be a set instead of some like curve or surface here. Okay, so that's the epigraph. Epigraph is defined as x and beta, where this beta is greater than or equal to f of x. So this is where beta is equal to f of x, and the greater than f of x means everything above it. So for every point, everything above it will be included. So that means this is the epigraph, and similarly this will be epigraph. Okay, and the definition is that if the function is convex, if and only if the epigraph is convex. Okay, or the definition, an equivalent definition for function f to be convex. Okay, let's look at a few examples. The first example is f of x is equal to x1 times x2. Okay, so for this function, the domain is defined to be the positive quadrant, so x1 and x2 greater than or equal to 0. So we first look at the domain. So I've put this domain on this slide. So this is x1, x2, and the omega is this area, right? The function value will be the third direction, which is popping out of this screen, and then the function looks like is x1 times x2. Okay, so as you can see, when x1 or x2 is 0, then this will be 0, and otherwise it will be something, some surface living on this plane. But it's pretty easy to draw the picture of this surface. Actually, it's not hard. But here I'm just going to show if this function is convex or not using the definition. So, for example, we first know that the domain omega is convex, so that's okay. But by checking the function f itself, we'll see that we're going to check if for every 2 point x and y, and for any alpha between 0 and 1, we can show that f of alpha x plus 1 minus alpha y is less than or equal to alpha times f of x plus 1 minus alpha times f of y. Okay. By the way, this is called a convex combination of alpha and y. x and y. Okay, convex combination of x and y, and this is called a convex combination of f of x and f of y. So by convexity, it's a special type of linear combination, but the alpha, you have to choose alpha and 1 minus alpha here. So these two numbers are both non-negative and they sum to 1. Okay, so that's the convex combination. So let's see that if this is true. Okay, now we can choose two special points. The first point is this 1, 2. Second point is 2, 1. So apparently these 2 points are in the omega, and we just need to check if the function value at this point is less than or equal to the function value at this point times alpha plus the function value at this point times 1 minus alpha. Okay, so first of all, alpha x plus 1 minus alpha y, you can check just plug in this x here and the y in here, or we can check that this point is here, and then the function value at this point is just equal to, according to the definition, f of x is just the product of the two components. That would be the product of these two, and that becomes this. And on the other hand, we can show that the f of x is equal to, according to this, f of x has two components, 1, 2, so the f of x is just equal to 2. And similarly, f of y is also 2 times 1, which is also 2. So we take a convex combination of the two, so it's just 2 itself. Okay, because if this is 2, this is 2, then you sum them up, you just get 2. And now you can see that can we make sure that this is greater than or equal to that number for all the alpha between 0 to 1? So that's the question. Okay, and then we can see that by taking a special value, alpha equals to 1/2. It is not the only point. Actually, other points may also work, but let's just say that the one point, as long as at one point this is not really greater than or equal to that, then that cannot be convex. Okay, so we plug in alpha equals to 1/2, then it's 2 plus 1/2 minus 1/4. We'll get equal to, right, when alpha equals to 1/2, we'll have 2 plus 1/2 minus 1/4, which will be 2 minus 1/4, plus 1/4, which will be equal to 9 over 4, right? So that means the this value is bigger than 2, so we actually have this greater than or equal to this. It's greater than this. So this is not always greater than or equal to that for all the alpha, but actually we can find some point such that it's actually greater than or equal to this, and that means the function f is not convex. Okay, so this is a way to, this is the easy example that we can actually name 2 points and check the convexity, use the definition. But in general, you can imagine that it's not easy, especially for high dimensional case. So that's why we're going to introduce several sufficient necessary conditions for function f to be convex. Okay, the first result is that if the function f is continuously differentiable, so it's C1, it could be from Rn to R, and C1, and the omega is convex, then the function f will be convex omega if and only if for any x and y this holds. Okay, this holds. This is a very important result and pretty useful in practice. It helps us to check if this function is going to be convex. The meaning of this inequality is that for every point x, you look at it for any other point y, you realize the function f evaluated at y is bigger than or equal to this. In 1D case, what this means, in 1D, what I mean by 1D is x and y are both scalars. Omega is just, say, interval on 1. And in this case, say we have x, we have y. For example, it looks like this. Then, if this is the x, let's see what is the right-hand side here. Right-hand side can be thought of as a straight line. passing through the point x and f of x. That means this point. So it's actually the tangent line at this point. So this line is like the f of x plus now the gradient of f is just the f prime, right? So I still write it in this way, but then in one decay it's just a y, just f prime at x. And then this curve actually means that. And the right hand side is actually function value. So for example, if y is here, so this will be f of y, okay, and this will be the right hand side. So this is left hand side, and this is the right hand side. So what this means is, if function is convex, if and only if for every point you draw a tangent line, and then the entire curve of the function f is above this tangent line. Okay, it doesn't matter where this x is and where this y is. This is always true. Okay, so that's the geometric meaning for a function to be convex. Okay, this is the case where f is C1, because we need the gradient. We need the gradient here. But the function f is convex, it doesn't have to be differentiable. For example, if I have a function like this, then it is easy to check that this is a convex function, because for any 2 points I can see that, say for example I have 2 points here, then I can see that the entire line segment is above this curve. Okay, or if I have x and y here, I can still see that the line is at least no lower than the curve. So this function is not differentiable. It's not differentiable at this point right here, but it's still convex. So the convex function doesn't have to be differentiable. But if it's differentiable, then it's convex if and only if this is true. Okay, this is true for any x and y. Okay, now let's see how do we prove this. Okay, to prove this, let's first show this direction. Suppose the function f is convex, then for any x and y, for any x and y in the domain omega, and for any alpha between 0 and 1. So now I don't really care about the alpha equals to 0, because I know that when alpha equals to 0 or alpha equal to 1, these two sides are equal. These two sides are always equal, right? Because when alpha, for example, when alpha equals to 0, then the two sides are both f of x. F of y. And if when alpha equals to 1, then both sides are just equal to f of x. Okay, so that's for alpha equals to 0 or 1, this must be true. I only care about the alpha between 0 and 1. So now, since I have this according to the definition that I have, according to the definition of convexity, I know this. So now I can move the I can subtract f of x on both sides, and then divide both sides by alpha. So when I subtract f of x on two sides, on the right hand side I will have this minus f of x. And here I have minus f of x. Okay, and that will be my numerator. So remember, note that I made a slight change to this one, just rearranged them. I put this, I should say, this is the y. This is the y here. And there should be x minus y. Okay, so I should I should have this y here, and the alpha of x minus y, and then I should subtract f of y on both sides. So I should subtract f of y on both sides and divide both sides by alpha. So I will get this. Okay, I'll get this. So by subtracting f of y on the right side, I will cancel out this term. But divided by alpha will be this. Okay, and this should be f of x minus y. Okay. Okay, so now, so I think in the beginning I should write this as 1 minus alpha. This is my as alpha. Okay, this is y is 1 minus alpha, this side is alpha, and also this side will be, that will be the one below. That will be easier. But let's just keep it in this way, and then let me see. I probably should still have to change that. Let's do this. I want to show that this will be 1 minus alpha. I will have this as alpha. Okay, and again, I can remember that you can always use 1 minus alpha on one, then the alpha on the other one. Doesn't matter. Actually, I prefer in this way. 1 minus alpha in the on x, 1 minus alpha in x and alpha in y. Okay, so once we have this, then we subtract the f of x on both sides and then divide both sides by alpha. And by that, I will see that here, this inside is 1 minus alpha times x plus alpha y. So I pull out the x and then I plus alpha times y minus x. Okay, so that's the term. That's the term here. So this becomes this. And subtract the f of x, and divided by alpha. That's my left hand side. And the right hand side, when I subtract the f of x, then we'll get rid of this f of x. So I only have minus alpha times f of x, and then alpha times f of y. So when both sides are divided by alpha, I know this is true. Okay, remember the alpha is here is the positive number. And now when I push alpha to 0, I will see that the left hand side, you basically can treat the left hand side as that, as phi of alpha, and that is f of x plus alpha y minus x. So right now x and y are fixed, and then for the varying alpha, I know that the f prime, the left hand side is actually equal to f of alpha minus f of phi of alpha, phi of alpha minus phi of 0, because in this case, when alpha equals to 0, phi of 0 is just f of x. Okay, and then I divide both by alpha. So you can see that this is a function, phi is a function of alpha, and I do this for alpha going to 0. When we push alpha equal to 0, then I know this is just a phi prime at 0. The phi prime at 0. Okay, so I know that if this is less than equal to the right hand side, which is this one, then we take the limit is still less than equal to the right hand side. That means the phi prime at 0 is less than equal to that. Okay, so every one of this is less than equal to right hand side, means the limit is also less than equal to the right hand side. So that's why I have this. So I know that this will be bigger than equal to the phi prime, like this one here. But the phi prime, according to the definition of our phi, when we take the phi prime of alpha, I will just get, using the chain rule, just the gradient f at this point x plus alpha y minus x times the derivative with respect to the inside, with respect to the derivative of the inside with respect to alpha, and that gives me another y minus x. And when I plug in alpha equal to 0, when this alpha is equal to 0, then I know this is just a gradient f times just a gradient f at x times y minus x. Okay, so now what I showed is that this is bigger than equal to this. Okay, so and then I move the f of x to the right hand side to this one here, I will get this inequality. Okay, so this shows that when function f is convex, then this must be true for any x and y. Okay, remember the only thing that the f needs to be differentiable, so we do have that gradient. Okay. Next, we show the other direction. So now suppose that the inequality holds. So suppose that right now the f of y is greater than or equal to f of x plus greater than f of x times y minus x. Suppose this is true for any x and y. And then for any given x and y, I can also define this point, define this x alpha. So this x alpha is like the point in between x and y. When alpha equals to 0 is at y, when alpha equals to 1 is at x. But for this point, I can substitute this y by x alpha, and then we'll have x alpha here, right? Oh, sorry, I can do this. I can do this as x alpha, this is x alpha, then I have this as x alpha too. Okay, so that's how I get the second equation here. Okay, and I can put any x and y here, so that's why when I put this y, just this y here, and x as x alpha, I get the second one. When I put this as x, and then this one x alpha, then this will be x alpha, this will be x, and this will be x alpha. Now I'll get the first one. Okay, just plug in different values for x and y. I get that. Now once I have this, I can see that when I multiply the first equation inequality by alpha, the second inequality by 1 minus rho alpha, what I will get. So first of all, this one is equal to, according to our definition of x alpha, this minus x will be just equal to 1 minus alpha times y minus x. And then this, when we subtract both sides by y, we'll get alpha times x minus y. Now, when I multiply both sides, when I multiply the first inequality by alpha on both sides, I'll have this as alpha, this times alpha, this times alpha. And the second one, I'm going to multiply both sides by 1 minus alpha, and also 1 minus alpha here. And I can see that for this term, I have 1 minus alpha, alpha, 1 minus x. And for here, I have 1 minus alpha, alpha, x minus y. So these two are negative to each other. That's why when I add these two inequalities right now, this term will cancel with this term. Okay, and I only have the sum of these two terms plus a greater than or equal to the sum of these two terms. But I do have this and this, the same term. So when I make this Convex combination of two equal numbers, then it will be just the number itself. So the right-hand side will be just f of alpha. Okay, and the left-hand side is this. So I know this is greater than or equal to this, but remember that x alpha was chosen in this way. So this here is just that. It's just f of alpha, f of x alpha. And the sum of these two will just give us this. Okay, so that proves the other direction.